Thanks. Good morning, everyone. I'd like to check the whether Dune is popular. Can you raise your hand if you're using it? Right? Cool. Yeah, pretty much everybody here. Okay, that's great. So if you're using Dune, you're also using this incremental computation library called Memo that we developed, and I would like to tell you a bit about this. This is. I'll try to. I have lots to say, but I'll try. Yeah. Okay. I'm going to talk about Memo, which is an incremental computation library. Yes. This is a joint work with many Dune developers, so I would like to thank everybody. Dune is an open source project, and we have many contributors. But I'd like to particularly acknowledge Arseniy, Alekseyev, who was working with me on this for like over 3 years. We'd like our build systems to be fast, and typically when we think about performance of build systems, we think about incrementality. So if you run Dune build and list of targets, you expect Dune to execute only the minimal set of external commands that needs to be executed, whose inputs or output changed since the previous time, since the previous build. And this is like very common in many build systems. But Dune also supports this file watching mode. If you pass --watch, what it's going to do is going to build the targets, and then it's going to wait for changes that you're making. If you edit the file, it's going to bring the targets up to date. And it's very convenient. And in this mode, we still care about this external incrementality. We still want to execute the smallest possible set of external actions to bring targets up to date, but we also start caring about internal incrementality. So we'd like to skip executing internal functions that don't need to be executed. We only want to execute those which depend on the file we've just changed. And Dune does quite a lot of internal work. It needs to read Dune files, it needs to generate rules, and it would be nice to be able to save as much of that work as possible during this incremental mode. And this is what I'm going to focus on in this talk, just the internal incrementality and how we achieve it. So to demonstrate it, I've tried to condense the Dune's build engine from thousands of lines of code to just 10 lines that fit on the slide. And I'm going to try to motivate all the features we want from this incremental computation library using this example. So we have the function to build a target on top. What it does first, it figures out where the target lives, the directory, and then it reads the Dune file in that directory because it specifies everything. It specifies all the rules for the targets that live in that directory. So we read the Dune file and we get a rule map back. So you can see the type signatures below. So you get a map from targets to the rules that you can run to build those targets. So we look up the target in this map, and if you find it, we call this execute rule function. And that function is what takes care of external incrementality. It will find the command that needs to be run. It will look at the inputs and the outputs, and if they are the same as in the previous run, execute rule will do nothing. Otherwise, it will actually run that external command. If there is no rule, Dune is going to check, is there a source file with the same name as target? And if yes, it's going to do nothing. This is the usual semantics. If you ask a build system to build a source file, it typically just says, okay, it's fine, I'm not going to do anything. But if the file doesn't exist, Dune is going to fail, complaining, you asked me to build something, but there is no rule for it, and there is no source file for it, so I don't know what to do. So this is to build a single target, and well, the user can specify multiple targets on the command line. So the way the Dune build command is implemented, we call this memo.parallel iter on the list of targets. Yes?
The fail width, is it the normal fail width, or I would expect a specific function to work in your memo abstraction?
You would expect.
Sorry, is it the usual fail width from OCaml' that raises an exception? And
so we use this memo library, and it catches the exceptions and wraps them nicely. So this is how Dune this is the idiomatic Dune code. Yes. What's maybe not obvious here is that actually there is a big recursive loop here. So execute rule can also call the build function because it might need to build the dependencies of whatever you're building. So everything is tied in a big recursive loop here. And the functions here are all in this memo monad. And this memo monad, you can think of a computation like a source file exists as a computation that reads the file system, performs some concurrency, and also maybe starts off external processes, and eventually returns you a value of a certain type, and that value may change between the different runs of the build system. All right, so now let me highlight a few important features that we need from Memo. The first one I just mentioned, we need support for concurrency. So if the user specifies 2 targets on the command line, the user expects them to be built in parallel if possible. And so as we like, there is nothing special here. It's a usual concurrency monad like async or LWT. You reach this execute rule when you traverse the list of targets, and it may spawn a new process. And at this point, that logical thread gets blocked, and you proceed to the next target. Nothing unusual. Sorry. The second feature we want is memoization. So if you are building two targets, they may be living in the same directory. So you might execute this read Dune file on the very same Dune file as another time. And we obviously don't want to duplicate any work. So this computation is actually memoized. So if you're going to execute it again, you're just going to get the value out of the hash table. And it may be not obvious, but memoization interacts in a pretty complex way with concurrency. So for example, if you started the external process in execute rule, and for the second target, you might end up executing the very same rule, because maybe a rule produces two targets, and you both requested them. So what's going to happen is that obviously you are not going to still have this result available in your memoization table, because it's still being produced right now. So what's going to happen is we are going to get blocked on this execute rule. We are going to wait for the result of the execution, and then continue. Another important feature is that in build systems, we want dynamic dependencies. So Memo must be a monad. We need to be able to discover our graph as we go. So it's not like we have our build graph known up front and we can memoize and execute it efficiently thanks to that knowledge. No, we have a bind, and here's how the bind looks in OCaml if you don't know, Simon. So this is like a Dune notation. So let star is essentially binding on the result of a read Dune file and getting the value rule map out. So we have a bind, and let plus, by the way, is map. Another important feature is error handling. So you ask a question like, what happens if you just fail with here? So Memo is going to catch it, but also like another interesting way, like this interacts with like concurrency and memoization, is that if you happen to read the same Dune file when building two different targets, and let's say Dune file is malformed and you hit a parsing exception, so that will be exactly the same error that you reached in two different ways, and you don't want to report it twice to the user. It would be very annoying to see the same error twice. So actually, Memo also needs to deduplicate errors. Not only it needs to kind of memoize successes and can somehow like avoid re-executing the same computation twice, it also memoizes like errors and also deduplicates them to present the user in a convenient form. And in addition to that, Memo also, by the way, attaches some kind of a stack trace to tell the user, okay, I failed when reading this Dune file, but why was I reading that file? And it explains to zero, okay, because you requested this target, and maybe that target like depended on some other target, and finally you've failed when reading the Dune file. And like finally, of course, we also want incrementality. So for example, here, if this like reading the source file exists, for example, it doesn't exist first, and you hit this error case, so you report an error to the user, and the user goes ahead and creates that source file. So what happens? We are going to re-execute this incremental computation, but only those like two lines are going to actually be re-executed. Everything else doesn't need to be executed because you didn't change the Dune file, so you can still reuse the same rule map. The only thing that needs to happen is we check whether the file exists again, and now it does exist, and we no longer report the error. So this is the incrementality bit. And well, incrementality is important for performance, but in addition to just making Dune incremental, we also put quite a lot of effort into performance tuning of Memo, because it needs to scale to quite big code bases. So you all raised hands that you're saying that you're using Dune, and we at JST would like to use Dune as well, but for now it's not still the main build system. And like some of the challenges we need to solve are due to our scale. So we have 30 million lines of OCaml code, and the incremental computation graphs that we are getting contain millions of vertices, and like one of them I remember seeing was like 100 million of edges in this incremental computation graph. So we had to put quite a lot of effort to make this run reasonably fast. So in the rest of my talk, I would like to just illustrate you how like various of these features interact on one particular example. So as I mentioned, there is a big recursive loop here where execute rule can build targets, which means that if you, for example, the user asks the Memo to build target 1 and target 2, and maybe target 1 depends on target 2 and target 2 depends on target 1, and I just told you that, well, if something is not yet ready, you're going to block on it. In this case, we are going to like hit a deadlock. And it would be nice to be able to detect such situations and report them to the user, instead of just like being deadlocked. And it's quite tricky in the presence of concurrency and memoization. And let me give you an example that illustrates why this is tricky. So let's say the user, I don't know, we are looking at this top-level memo parallel iter kind of task, and Dune starts executing it, and there are two logical kind of threads that happen, and they keep executing, and at some point, like the red thread wants the result that is being computed by the blue thread, and I'm using two kinds of errors here to indicate that something different is happening. The plain arrow is a forcing edge. It means like this is the first time you've come to a computation and you are forcing to evaluate it. You don't yet have it in your memorization table. And an arrow with a diamond is a blocking edge. So you've come to a computation, it's not yet ready, it's currently being computed, so we need to block and wait for the result. And well, you probably guessed what is going to happen. Blue now wants the result of the red thread. And so we are in a deadlock, and there is no obvious local properties that like these threads can check to figure out that they're in a deadlock state. So like what do we do here? So the problem that we need to solve, we need to be able to detect for cycles as the graph is being grown, and like various like edges and vertices are being added to it concurrently in various places. And like a naive thing would be, so we have a graph. Whenever we add a new edge to it, let's just check for cycles, and that would work. It will be quadratic in the number of edges in the graph. It'll be very slow, as I mentioned. We have like millions of edges in our graphs. So we've been looking for a solution. We found an incremental cycle detection algorithm by Bender et al. It's a fairly recent one. And like one particular reason why we were interested in using it is because there was an OCaml' library that implemented this algorithm, and not only it was working, it also was proven to be correct. It was like derived from a Mokhov proof of correctness, which was amazing. So we started using it. But so it's better than the naive version. It's instead of m squared, it's m square root of m, and it's kind of still too slow just by itself. If we just keep adding everything that we have in our graph to this cycle detection incremental data structure, it's still going to be pretty slow. So the first idea, the obvious one, just add all the edges that you have in your graph. It just doesn't work for us. So the second idea was let's not add reading edges. So this is a new kind of edge which I added on the slide. It's where you come to a node, but it's already finished. Somebody like else has already computed it, so you can just read out the value and continue. So these edges cannot possibly appear on cycles for the quite obvious reason, because if something has already been computed, it doesn't participate in a cycle. So these edges don't need to be added to the cycle detection graph. And that was already quite a good improvement. Dune was using this like second idea for a long time. It was still annoying because it was still taking 35% of incremental zero rebuild. So you change like one of the files in a trivial way that doesn't cause any recomputation, but still Memo needs to traverse the graph and it still needs to check for cycle, and it was taking like roughly 1/3 of the computation time, this checking for cycle. And this was like very annoying because the cycles happen fairly rarely. So we obviously want to be able to detect the situation, but we don't want to pay like much for that uncommon case. So we came up with another idea. So on this graph, there are still some paths here on the sides that we are adding to the cycle detection graph, but they were not interesting because there were no blocking happening there. And the danger, like you're in danger whenever you block. So the idea was, okay, let's add new edges to the cycle detection graph only when we hit a blocking edge, and we're going to add that blocking edge as well as the path, the call stack that led us to that edge. And we already have the call stack available because, as I mentioned, we use it for reporting nice error messages. So it was like very straightforward to actually implement this idea. And the good news is that it's much faster. In fact, checking for cycles now disappeared from our profile. It like roughly takes 0 time, and we are super happy. It's much harder to prove that this is correct. We don't have a Mokhov proof. So maybe so we have a proof that that library is correct, but whether we use it correctly or not, it's an open question, and I hope that we do it. So it would be nice to get some help from theorem provers in this room. So can we do somehow better? Like we don't need to do better in terms of performance, I think, because now we are happy, but maybe we can do better in terms of simplicity, because this is still quite a complex algorithm to use. So this is like just one of the examples of the complexity that went into implementing Memo. So we use it in Dune. It's been used it's been developed for more than 3 years. And this version with the cycle detection, with this fancy cycle detection algorithm, was used for more than a year, and we didn't hit any issues. So we are fairly confident that Memo works well. And it would be interesting to see like other users apart from Dune in the OCaml community using this Memo library. One like complication on the way there is like Dune uses its own concurrency library. It's called Fiber, so it doesn't use async or LWT because Dune needs to be small. It would like to avoid depending on any libraries. So it has its own concurrency monad. But you could turn Memo into a functor over an arbitrary concurrency monad. So you could use Memo with the monad you like. It doesn't seem to be like very complicated. So if you'd like to use Memo and you want to use it with a different monad, talk to us and we'll try to make this happen. And there's also a lot more performance work that's happening. So as I mentioned, our graphs are huge. And the last time I was profiling a Memo, probably not surprising, most of the time was spent just waiting for memory because we are like traversing this huge graph. Like we are never getting the cache hits. So okay, we need to figure out what to do about this. Like one idea is maybe we could try to flatten it somehow. We also have some ideas of how to. So right now, Memo is based on basically traverses the whole computation graph on every incremental rebuild to figure out what nodes have changed and which nodes have to be recomputed. There is an alternative approach to incremental computation libraries, which is used by libraries like incremental or adapton, is where you initiate recomputations from the leaves. So if you know that this particular leaf changed, you start propagating the changes. But there are some trade-offs, like you need to store reverse pointers. It makes your kind of garbage collection story harder, etc. So there are a lot of other work we would like to do. And of course, at some point, we would like to use multi-core OCaml as well. So because, like as I mentioned, Dune has a lot of internal work. Maybe we can parallelize it. All right, some help on proving that this idea works would be also helpful. So Dune is open source. You can find Memo by following this link. I'd like to also advertise this paper, which has this formal proof of correctness of the cycle detection algorithm. I found it very nice. And in general, if you're curious about the challenges, the kind of challenges we are solving on those systems, there's a paper we wrote on that describes the landscape of those systems and what problems are there and what problems need to be solved. So thanks. I hope you enjoyed it.